We're going to continue on normalizing steels. So what are the reasons to normalize steel? Is to produce a harder steel when compared to fully annealed. And over here we're going to address why this is the case. Why is it that in normalized steel is harder, and also it has relatively good ductility without significant loss in hardness for normalized steels. And in normalized steels, the rate of cooling is dependent on the mass, surface area, and thermal conductivity, because it will affect the thermal diffusivity, which is a function of thermal conductivity, density, and specific capacity. So we're going to see the effect of why or the effect of normalized, fully annealed, and normalizing. On the left hand graph, you'll see the effect of percentage of carbon with yield strength, and on the right column, it is on percentage of elongation. As you can see, with higher percentage of carbon, okay, when percentage of carbon increases, normalized steel tend to have higher yield strength. Okay, as I say, we're going to explain why. Whereas fully annealed, it just plateau down over there. And if you were to look at in percentage of elongation, fully annealed, okay, or normalized, the percentage of elongation will go down much lower than fully annealed. So why is this so? Okay, so as you know that normalizing, you don't have control cooling of the surface, so the surface temperature cool quicker than the core. So when that's the case, higher percentage of carbon will increase the tendency to form what martensite under rapid cooling. Okay, and carbon has insufficient time to diffuse. So if we were to look at the surface, okay, we look at the surface and the core for normalized and fully annealing. Normalized, you have martensite on the surface, and the core you have ferrite plus cementite. When you do full annealing, the surface and the core have the same microstructure. This explains why, especially at higher percentage of carbon, the martensite yield strength gets higher. Okay, so when the steel is fully annealed, the microstructure is uniform from the surface to the core. This is due to what? Control cooling. So this is an illustration. Okay, so if we look at the black, okay, so if we focus on carbon less than 0.77%, the surface and the core are both ferrite plus cementite, ferrite plus cementite, and this is for fully annealing. Okay, this graph represents all for fully annealing. And then if the carbon of percentage of carbon is greater than 0.7%, you will form cementite rather than ferrite at the surface, and the core also gets cementite plus ferrite plus cementite. Okay. So however, in normalizing, the microstructure will not be homogeneous from the surface to the core. So if you look at the percentage of carbon, that's 0.2%. This layer over here that you can see, that you see the pink, this layer is a martensite, whereas the core is ferrite plus cementite. Whereas when its carbon is 0.9, higher percent of carbon, the tendency to form martensite is higher, because upon cooling, you don't allow carbon to diffuse, so you get martensite formation. So the martensite layer become what? You have higher thickness, okay, with higher percentage of carbon. So just to recap, right, we know that during full annealing, the core has pearlite and ferrite, and the purpose is to absorb the impact loading. So pearlite and ferrite have better loading. Okay, so this is why we have pearlite and ferrite at the core. Now, fully annealing is preferred when homogeneous microstructure is critical, and full annealing is more costly when compared to normalizing. Okay, this is because of due to time that's required to during controlled cooling in a furnace, and most important of all, when percentage of carbon is less than 0.4%, both full annealing and normalizing will generate similar mechanical properties. So, i.e., less than 0.4, does not matter. You can do fully annealing or normalizing, the properties will be the same. So to lower the cost, you'll prefer to choose normalizing. Okay, so that's it for the continuation of normalizing.